you just like really see Lean wandering in the wilderness, Leo DeMora and this band of mathematicians wandering in the wilderness, and they achieve something, and suddenly it is exactly, it's like, well, the superhero the world needs by the time they come back home.
Welcome back to Breaking Math. I'm your host, Autumn Fanaff, joined by my co host, Noah John Syracuse. For over a decade, this show has been about one thing: finding the math hiding inside stories that actually matter. And today's story is all of that. A small group of mathematicians who walked away from their careers they'd already built to bet on a piece of software almost nobody thought would work. Neither a funding push nor a big lab behind it. And it was simply a programmer at Microsoft who didn't even consider himself a mathematician, and a handful of people willing to follow an idea for years. And this looked like it was going nowhere. That software is called Lean, and it's becoming one of the most important tools in how AI systems verify whether mathematical proofs are actually true. It checks proofs line by line, the way a computer checks if code runs without a bug. Our guest spent years embedded in that story. He's a journalist who's been covering Lean since 2020, all the way to present day when it's sitting at the center of how AI and mathematics are colliding. His new book is called The Proof in the Code, and it's a very human story that everyone should read. So please welcome Kevin Hartnett.
All right, before we get rolling here, I just want to tell our listeners a little backstory, which is I joined the show several months ago, and Autumn has been involved in the show for many years. But I recently learned that your first episode in front of the mic, rather than behind, was actually on Lean, the topic we're going to hear about today. You were
Ironically,
explaining an
yes.
interesting story about Lean being used in chemistry. So yeah, you didn't really have to research or prep for this episode. You already knew it. So that was really cool. I, on the other hand, came to this fresh, not knowing anything about it. I read Kevin's book. Autumn and I had the same reaction, and I'll just say this. We read a lot of books for the show. Kevin, your book just stood out. It was the best math book I've read in years. It was really like magical. And what struck me was probably, I mean, I think it's safe to say maybe the best math book ever written is James Gleick's Chaos. I think no one's going to shoot me for saying that. It's just absolutely amazing. That really inspired, I'd say, a whole generation to get into math. Maybe it helped develop Jurassic Park, who knows. But what I loved is your book had a similar spirit. It really was this, or is this confluence of events, this happenstance of this thing happens and this thing happens, and this whole new way of doing math and thinking emerges from this very like circumstantial experiences that somehow when you look back feels inevitable, but you tell the story of how so much fluke was involved. And it's so character driven. It's so exciting. I learned so much. So we don't normally recommend the books. We just jump in, but I couldn't resist it here. Please, please, please read Kevin's book. It's absolutely amazing.
Oh, thank you, Noah. It's wonderful to hear that.
And that sets the stage for our first question, which is, why did you decide to write the book now? And let me even elaborate a little. It is such an amazing story of how Lean came to be, but the story of Lean is still being written. And this must have been kind of stressful for you, where I'm sure as you were sending in your final manuscript and draft, every day there was a new development around Lean. So how did you decide this was the moment to stop collecting material and put it out there?
Absolutely. So I first wrote about Lean in 2020, an article for Quanta magazine called Building the Mathematical Library of the Future, about the building of MathLib, this kind of repository of formally defined math concepts that you can draw on and call on when programming in Lean. So I wrote that 6 years ago now. I wrote a couple follow-up articles within a year after that, and then did not think too much about the topic for a while until 2023, late 2023, when Quanta Books, my publisher, was born. And I was talking with the publisher of Quanta Books about topics, and we came to writing this book about Lean. The reason we wanted to do it then was it was clear Lean had achieved a kind of escape velocity in mathematics. For years, it had been this somewhat marginal effort to get mathematicians to adopt this new digital way of working. It was not clear whether it would succeed. That's a lot of the drama in the book. The years it covers is like 2013 to almost the present. But in a lot of those years, it was not clear whether lean would ever be widely adopted among mathematicians. By late 2023, when I started this project, it was clear it was here to stay. And I think that gave us confidence that this book would be covering a topic that would be relevant, very relevant in math for years to come. As you say, though, even during the year and a half I was writing the book, this story changed a lot. It's still changing a lot. There's like almost a whole different book to be written about lean. We can get into that, and I can even talk to you about why the breaking point was where it was. But anyway, lean is here to stay, and I think that was like clear in 2023 and why we wanted to do the book now.
Now, I'm curious, you have a whole story about a computer program, but at what point did you realize that it wasn't just a technical story, but it was actually more of a human one?
Yeah, the characters behind it have been compelling from the start. They were some of the people I met when I reported that first article in 2020, especially the mathematicians who took to lean first. The book follows a small group. There are probably 4 main characters who most of them had fairly successful research math careers. They were kind of in a mid-career phase, and they could have gone on being research mathematicians the same old way. But for different reasons, they were drawn to this program, to this new way of working in math. They kind of abandoned their research lines and really gave themselves over to developing the underpinnings of it and also to evangelizing it among their colleagues. And the kind of the aspects of their personalities that drew them to it, like why now, why choose a new way of working, had always been the most appealing part of the story to me. The kind of new element of the story for me was getting to know Leo DeMora, the creator of Lean itself, who's not a mathematician, and understanding kind of his motivation and why he really devoted himself at great risk to his career as well for more than a decade. So it was just clear that all these people could have taken a kind of an easier path, and they didn't. And I wanted to make sure the book got across why.
And I think you do such a great job of, there's been other works that do this, but yours is such a great addition of really showing that math and science more broadly doesn't happen in a vacuum, right? There are people behind all these things. There's history unfolding. But now that we've kind of set the stage with why your book and when your book, let's get into the meat itself. So for someone who's very new to the topic, I would say mathematics is among the most formal ways we have of writing and communicating. So why the heck do we need to formalize something that's already so formal? And what does it even mean?
Yeah, it's a good question. So I think most people who have never written a math proof or even kind of read one necessarily, maybe you have this idea of the way math is done on the chalkboard. You kind of can picture like lots of symbols that you can't really read, and it feels like super technical as it is. I think the key thing to understand is, so math advances through proofs, logical arguments from which conclusions fall out. And those conclusions are just new facts that get added to the mathematical canon. And then those facts can be used in yet new proofs to create new facts. But proofs are logical arguments in which each step follows from the one that came before it. When you see a chalkboard proof with all those symbols, mathematicians are leaving out most of the steps. They're just like broad strokes of an argument. And they can do that because they generally understand how concepts relate to each other. They know that, yeah, you can do this and then get blah, 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 blah. Yeah, that always works. And then you can do this. They don't have to spell it all out. A formal proof is where you really spell out in exact terms every single step in the argument, exactly the way a computer program works. And that's like kind of the comparison that's important to have in mind. So a computer program lines a very well-specified instructions to your machine. Each line follows from the next. You can't skip lines. The computer can't kind of just like, know, oh, I can do this and fill in the blank for itself. You need to tell it exactly what to do at every step. If you do that correctly, your program runs in a bug-free way. If you write a math proof at that level of detail, where you specify every little instruction, every step in the logical argument, as I say in the book, the proof compiles at the end. It kind of runs in the way a program runs. And if it does that, you know it's correct, that the logic holds together. So it is, in fact, quite different to write a proof in a programming language like Lean than it is to write it on a chalkboard. There is this ratio mathematicians refer to called the De Bruijn factor, which is the ratio of lines of computer code you need to express a kind of an informal PDF or chalkboard math proof. And it can be 20 to 1, 100 to 1. So imagine almost in many cases, there's let's say 20 to 1, 20 times more lines of computer code required to formally write a math proof that you would write compared to writing it informally in these other mediums.
Makes me think a bit when we all take math in high school, we take geometry, and you go through all these very tedious triangle theorems and proofs, side angle side and this and that. And you write out every step with all these vertical angles. And at the time, it's just so pedantic that you have to number and label every step. And if you continue in math, like in college or beyond, it's such a relief. You can just like think and be free. So it's kind of funny that lean in this formal math, it's kind of really is going back to high school geometry where you have to write every single line.
It is like that, but also mathematicians talk about the tedium at different points in writing a proof. Like, there's definitely a moment where they're thinking and being free and coming up with big ideas and seeing the kind of the pillars of the argument they're going to make. I think they might consider that the most exciting part of a proof, but often there could be years of kind of getting the technical details nailed down. One thing they like about Lean is it offers some relief from that tedium potentially, because where you have these technical pieces you need to implement, Lean can help you do that in some ways, like a little faster than you could when you had to do it on your own.
So Lean began in the early 2010s with Leo DeMora at Microsoft, correct? What problem was he originally trying to solve, and how did this lead to this larger transformation for mathematics?
Yeah, that's a very important question. So Leo was at Microsoft Research. He is not a mathematician. He was not interested in mathematics. He wanted to create software for eliminating bugs in computer programs, for catching bugs in programs like Excel, new versions of Windows. And there are a few different ways to do this. One is to essentially kind of test the program very thoroughly and see if bugs emerge when you use it in various different ways, and then you clean those up. You can catch a lot of things that way, but you can't create guarantees that there are no bugs. There's been this vision for a long time that you can write computer programs in this formal way where you specify what the program is supposed to do. You create a specification, which is kind of like a conjecture in math. And then you treat the actual code of the program as a potential proof of that conjecture. And a piece of software like Lean can tell you whether the computer program exactly matches its specification. Does it do exactly what it's supposed to do and nothing else? That can give you a guarantee of correctness, which lets you feel like there are no big security vulnerabilities. Leo wanted Lean to be an environment in which you could take big pieces of software like these Microsoft programs and guarantee that they contain no bugs. That's why he initially built the program.
So, Kevin, here's a point where I really want to drill down and understand, because I feel like I've read a lot about lean at this point. Your book was, fantastic source, but something I still feel like I'm a little bit missing, which is, let me draw from the AI literature a fun example. Probably most people have heard of this paperclip maximizing problem, right? That you tell some super smart future AI
Right.
to make paper clips, and it figures out, oh, I can turn humans into fuel for this, and all of humanity's dead. So this is not technically a bug, but it's a misalignment, right? I just want the stupid thing to make more paper clips, and I ended up
Mhm.
wiping out humanity. So when I hear of these guarantees, like, oh, we want to formally verify and make sure the software does what it's supposed to, I'm not a computer scientist. What I have in my mind is, what about these sort of misalignments? Like, technically, the AI did what it was supposed to. It made paper clips, but it didn't do what we intended. So does lean help with capturing that intent, or is it just some kind of mechanistic thing that's separate from human intent?
So one of the reasons that formally verified software is not more widespread is, I think, precisely because writing a specification for many pieces of software, like exactly defining what something like MS Word is supposed to do, is difficult. And I think you could end up with these pieces of misalignment. So no, lean is mechanistic in that sense. It does not take care of the difficulty of kind of specifying exactly what it's supposed to do when a program is used in a kind of more amorphous way. So you still have to worry. You might still have to worry about paperclip maximizing.
All right. So it doesn't save humanity just yet.
It might, but not in that way.
Not because of that.
No.
So, doesn't Lean start from almost zero knowledge and build up for definitions, libraries, and then go to previously verified results? Or what's the process of that?
Yeah, so a lot of the book is there are kind of like two parallel efforts that ultimately meet and are very important to have in mind. One is the development of Lean itself, the software program, and this is something that Leo did almost entirely on his own, working at Microsoft Research in this like very driven, visionary kind of way. The other is that the mathematicians, who for various kind of almost chance reasons became its first and most active users, they start wanting to write math proofs with it. They realize Lean, as you said, doesn't know any math. Like Lean is just a kind of an environment in which you can type code. It knows some basic axioms of math, but it doesn't even know like what the rational numbers are. It has no notion of a prime number. It doesn't know what complex numbers are. It certainly doesn't know like calculus out of the box. If you're writing a math proof in Lean that draws on any of those concepts, let alone kind of higher order concepts, you might have to recreate them in the Lean language every time you write a proof. Every time you write a proof that involves the complex numbers, you might have to redefine what the complex numbers are. That is like kind of tedious. No one is going to really use Lean if you have to do that. So there's this parallel effort to create this thing called MathLib, which is like a digital library of math concepts, definitions of objects, theorems that have already been proved, lemmas, like little mini theorems that have already been proved. And so if you're a mathematician and you boot up Lean and you want to write your proof in that environment, you don't want to have to write out all of these like underlying elements. You can call on MathLib, almost like retrieve these objects from that library and say like, insert complex numbers here, insert this previously established theorem here. It lets you write your proof much faster. When Lean starts, though, MathLib doesn't exist. There's nothing to call on. So there's this pretty monumental effort by a small initially, but then over time expanding group of volunteer mathematicians who try to create this digital library of mathematics, MathLib. And what they view is the kind of the right, most future-proof way so that down the line, any mathematicians trying to formalize any kind of math proofs, the library will be useful to them.
One of the stories I love in your book is this whole idea of how do we shore up the foundations of mathematics itself, right? Going back to Leibniz, you mentioned calculus. So Leibniz was interested in this mechanistic idea that maybe not just math, but everything can be kind of rigorously formally proven. And zooming up to the early 20th century, we have Hilbert and the foundations of set theory and Cantor and all this revolution where people realize math has a lot of holes in it, right? These paradoxes, and we really need to build a theory that accommodates those. So Lean is put in your story, and I think rightly so, as this legacy of trying to make sure math is accurate, correct, that there are no gaps, no logical quandaries we could fall into. But again, very naive question, but I have to ask because maybe listeners have the same thing as me. How do I know? So I understand the idea that Lean is going to help, we can verify things are true. How do I know some summer intern undergraduate didn't actually type one definition a little bit wrong when formalizing it? And now, our foundations are shaky because we didn't type in one little aspect of MathLib quite right.
Yeah, so this is actually a kind of deep question that comes up in the book and still comes up today with mathematicians working in MathLib, which is like, you define something in this special language. It's not the same language you're using to think about it. How can you be certain that the definition as Lean understands it matches your own understanding of the concept? And this comes up in this significant formalization effort called the liquid tensor experiment, which was led by Johan Kamelin, who is one of the leaders of MathLib and one of the main characters of the book. The liquid tensor experiment is a multi-year effort to create a formal version of some work by Peter Schulze, one of the most accomplished living mathematicians. And Peter is not himself a Lean user, really. He comes to Lean in order to just like verify the correctness of some work he's done. He is talking with Johan as Johan tries to formalize Peter's work. And at some point they have this discussion, and it's about exactly this point. Like, how can I trust these definitions? How can I be sure the summer intern, or I guess in this case, Johan, did not have the wrong keystroke or misunderstand things? And Johan establishes this kind of, he refers to it as like this kind of like this rule that if a definition walks like a duck, quacks like a duck, it is a duck. That is, if it behaves when you're trying to write proofs the way you anticipate the definition should behave, you can have a lot of confidence that the definition is correct. So I think like that errant keystroke you talked about, very quickly you would find, if you're a mathematician, you're trying to draw on this definition, it's not behaving in your proof the way it's supposed to do. You can't establish the conclusions you want to. That is where you start to gain that confidence that the definitions are in fact aligned with your own understanding of the concept.
So do you think it's fair to say we're not guaranteed that we have completely accurate foundations of math, but it's much more probable than we did when we did it by hand?
Does lean make us more confident in the foundations of math? I think there's some very existential philosophical questions that you could still ask about the foundations of math.
Sorry, I don't
I
even mean like setting them up, but like, a theorem that's published in the literature. So
Yes.
are we more
So,
inclined to believe it if it's built on lean foundations rather than human published literature
I
foundations?
see what you mean. Right. So there are, if a very specific theorem or proof has been formalized in lean, I think there's much greater confidence that it is correct than otherwise. Now, in many cases, mathematicians are not suffering these like crises of confidence. Like they generally almost always know when something is correct or not. There are particular cases where there might be some doubt about whether a theorem is correct. This was the liquid tensor experiment. Peter Schulze had some doubt about his own theorem. There's currently this somewhat high profile effort to formalize a very large paper that's been around for more than a decade, where there's like a lot of uncertainty about its correctness, or people kind of doubt its correctness, but they've not been able to like nail that down specifically. Turning to lean then in order to like put the paper in lean, see if it compiles or runs in lean. Yes, that does give a much higher degree of assurance in these cases where, for a variety of reasons, it's hard to pin down.
So there were many people who needed a formal verification for their proof systems. Now, I know that Kevin Buzzard actually becomes a really important character in this story to build out this program, but something that any new system has when you're trying to onboard people is a cold start problem. Did this software actually have that issue? How did we get more people involved in it? Tell us about that a little bit.
Oh, yeah. I mean, the cold start problem is like a super relevant here. What type of program is lean? It's called the interactive theorem prover. You interact with a computer, you prove a theorem at the end, an ITP. These have been around for a long time. One of the most kind of significant ITPs before lean is this program called COC, now called ROC, that was created in 1989. There are others, a number of others. None of them ever achieved breakout status among mathematicians. They kind of they tended to just be used by small communities. The field did not adopt them widely. In my book, I talk about how getting lean to be a more common tool for mathematicians was both like building MathLib, which just made it more useful, made it more feasible to formalize work, and it was convincing other people to give it a try. That was kind of one of the most important elements of its, would it succeed or not, was can this small group of early adopters, 4 people, 10 people, a dozen people, each convince other people to do it. In the book, I have a chapter about kind of a breakout moment, which was around the pandemic, when a lot of people had to adopt new ways of working, right? Everyone was suddenly online all the time. One of the first big lean user conferences was already scheduled to take place before the pandemic started. Then the pandemic hits. They have to quickly try to do it on Zoom. There's like a scramble behind the scenes to figure out how are we going to run this event. They're also getting more and more people signing up because more and more people are now like at home and have time to kill. That type of effort where you create a conference, you try and train a few people on how to do it, you try and you do a new conference, they train more people, is essential to lean's growth among mathematicians. And so, I mean, I talk about the kind of the curve and user adoption. You could think of it as exactly the way you would imagine like the curve of user adoption and like in a social network. It kind of slow, and kind of like starts to take off. That was definitely lean's experience through the period covered in my book. And then it's inflected even more since then.
When we're looking at the formalization of new papers, do you think that there could be a future where major mathematical papers are expected to come with a lean verified version? Where is this going to be taken off into the future? I know that this is something that's a little bit past your book.
No, it's a
But
huge
I'm
topic, and
curious in that
I do have
direction.
a number of thoughts on this. So, okay, why would mathematicians have been so lean? Sounds great, right? You can like write a proof in lean, you automatically know it's correct. Why would everyone not do this? Well, the reason mathematicians didn't want to do it is like many don't doubt the correctness of their work, or they feel like the community can tell them if it's correct. So they don't see like the value proposition. Also, it's like quite tedious to like turn a proof into a program, to rewrite it in a programming language. I mentioned that kind of ratio at the start. Writing a normal math proof in Lean takes a lot of effort. So that was like, and you have to like learn this very fiddly technical language in order to do it. That was a major barrier to adoption. Things are changing right now. And the way in which they're changing, of course, as I think people are broadly aware, AI is very good at writing computer code, all sorts of programming languages. It's much easier now to take a paper written the old-fashioned way and convert it into Lean code. Either like you can kind of have within Lean, a kind of co-pilot mechanism where you are doing the programming yourself, but you can kind of invoke the AI in places and have it fill in parts for you. Or increasingly, you can just feed a paper into AI and have it translate it into Lean code automatically, the same way you might have a research paper you wrote translated into another language, like, Spanish to Chinese. You could translate a LaTeX PDF, which is LaTeX is like the word processing language mathematicians write their proofs in. You could translate that into a Lean proof automatically with AI now. So the barrier to having a Lean version of a proof has gone way down. Will journals increasingly ask mathematicians to submit their work as a Lean proof so that it can be refereed automatically, checked automatically by computer? I think there are indications that that will be the direction the field goes in. It's especially true, and maybe we'll get to this later, for proofs that are not even written by mathematicians, but are written by AI, which is like an increasingly real thing, AI generating proofs. And Lean is a great way to be able to check those proofs without having to kind of go line by line through what is kind of an increasingly large volume of AI generated material.
I think you took the next thought right out of
Yeah, no, let's go there.
my
What do
mouth,
you want to talk
especially
about?
because everyone is using AI verified this, AI verified that. And it makes me wonder, once a theorem is formalized in Lean, even if it's done by AI, is this something that is just hands wiped, step away from it? Is it done forever? Or are we going to have to add that to MathLib and essentially maintain the software?
Yeah, so there are a lot of aspects of that question to dig into. One thing I will say is that when you have a proof and you have it automatically translated into Lean language, the technical term for it is auto-formalized. That AI produced Lean code is not going to be at the standard of the code that is accepted into MathLib. And this is an important point about why Lean, I think, has been successful, is because the people who originally created MathLib and oversaw its development and vetted new potential additions to the library had very high standards for how things were defined. So when you have an object in math or a theorem, there are many different ways you can write it typically. And they're called the maintainers, the kind of people in charge of MathLib, held a very high bar for what these new objects committed into MathLib should look like. They wanted them to be very elegant, so they didn't want a lot of like extra terminology that didn't need to be there. They wanted them written at a very high level of abstraction and generality, so that these objects are not just defined in the particular way they're used in a particular proof, but in kind of on their own terms in this general way, so that any future proof can kind of very readily use them in its own work. So MathLib had these high standards, push towards abstraction, generality, and elegance in the way objects were defined. And AI auto-formalized proof is going to have all the same kind of sloppiness we're kind of accustomed to see from LLMs when they output just like text to us in a chat. So if we formalize a proof automatically with AI and we have all this Lean code, there's a whole nother step of digesting it, refining it to make it essentially MathLib level before it could go into MathLib. And the mathematical community is just now becoming aware of the need for that step, and the community to kind of develop mechanisms for digesting proofs in that way. They're figuring it out right now.
It's funny, this the maintainers makes me think of almost like Autumn. You probably know about this. There's the French language academy that like officially maintains French. I remember learning about that in high school.
Oh yeah, they really are
Yeah.
gatekeepers, and like
It's amazing.
they when people would come into Lean early on, say around 2019, 2020, 2021, often the first step is there was some ways to start learning the program. This thing called the natural numbers game, which is a game Kevin Buzzard created where you define the natural numbers in Lean. It's just a way to kind of get your feet wet, get a feel for it. But often the first kind of rite of passage for any new mathematician interested in Lean would be to formalize something MathLib doesn't contain, and no one would get it right, just about basically right, on their first go. They would formalize something, and then the maintainers would give them notes back and say, try again. So they were very strict gatekeepers, and it was, like I said, a rite of passage for new entrants into the Lean community.
I want to ask a question that I think might be a little bit tricky. So feel free to just think out loud and tell us what you think. Because I don't know if there is a good answer to this, which is if we just step back a couple years in the history, which your book beautifully tells, there's this amazing adventure. I think it was largely centered around Google of developing these AI systems that are really good at math. And kind of one of the ideas that goes into it is reinforcement learning has been so valuable. You can teach a computer to play chess, not by just feeding it tons of scripts of chess games, but you let it actually play chess and learn from its moves. And with Lean, now you don't need a human grader to tell it when it's doing correct math or not, right? The AI can try lots of math things, try approaches, and it gets instant feedback through formalization, for verification, I should say, whether it did a correct move or not. So it seems like the perfect environment to do reinforcement learning and to build this kind of mathematical super beast that's really great. And I think that is what happened, right? Google did very well in the Math Olympiads. But what I think is going to be a hard question is, right now, at the time that we're recording, I would say the biggest mathematical result that's been attained through AI, in many people's opinions, is the Erdos unit distance conjecture. On the show, we had Daniel Litt just a few weeks ago to talk about this. That was discovered by ChatGPT in what OpenAI is claiming was a fully general purpose system that, as far as we know, did not really involve Lean. So my question is, if Lean is so helpful for AI, why is ChatGPT's system that doesn't use Lean comparable and maybe even in some ways beating these systems that are really designed to leverage Lean?
That is a good question. It's one I recently, within the last 2 weeks, had a panel discussion online with a number of the members of the MathLib community and asked them that question. The answer will echo an answer that Jeremy Avigad, a professor at Carnegie Mellon, and one of the main characters in my book, gave me, which was going forward, he expects it will be kind of a combination of informal LLM-based proof generation like the OpenAI proof you just talked about, and systems that are searching for proofs where they use Lean to verify outputs. I mean, these are all going to be LLM-generated proofs. The question is, do you translate them into Lean in order to kind of check their correctness? Conceptually speaking, it seems to me that Lean is going to be an essential element to this because the key thing that makes LLMs useful is they are capable of generating lots of ideas, exploring lots of paths, like that scale is what makes them so powerful. And if you have an LLM generating, orders of magnitude more proofs, how are you going to know which ones as a human you should then spend some time investigating? I don't know how focused the team was at OpenAI on this particular thing. Or kind of how many candidate proofs they had to sort through before they found the right one. But I think in most cases, it's like a little bit of a search and verification process you need to run. And that verification process is going to have to be backstopped by something like Lean. So it strikes me that it will be critical to kind of math research with AI going forward.
So maybe like a condensed version of what you said, which I think is absolutely spot on, is that the just kind of vanilla LLMs without Lean necessarily are really good at idea generation. And in this case, OpenAI had professional mathematicians that could look through these ideas and say, this is a really good when it works. But in general, LLMs are not so good at the self-policing, and that's where Lean and things like that come in.
Right. So I think kind of lean and that reinforcement learning, that self-checking is what lean will be really good for. A point actually I wanted to make that I would have made like 5 or 10 minutes ago, but I think is important to get out is so the book ends really kind of pre um, widespread understanding of what AI can do for math. There's a chapter about Google DeepMind at the 2024 IMO, International Math Olympiad, the most prestigious pre-college math competition where Google DeepMind, their system AlphaProof, achieves a silver medal level score. But that was in the summer of 2024. It was really only in early 2026. So, not many months ago that we really began to see AI solving open math problems. And so the story of lean, as I tell it in my book, it changes a lot. It changes a lot, and it changes a lot in the last 6 months. So an interesting thing to me, two things. One is just there's just this kind of perfect confluence between lean and our AI moment, both like what AI can do for math and also AI generating computer code that we might want to have more confidence in that lean can be used to check. So like lean is just an extremely useful tool for the capabilities and also kind of pitfalls of AI today. I asked Leo recently, like, what he imagined the trajectory lean was on if kind of AI had not taken off the way it has, really over the last year. And he thought it was going to be kind of a going concern as a niche tool. I think he used the word niche. And he thought it would be successful, it would have its users, but it would remain niche. Now we're very much seeing it's like a much more generally useful tool with like a lot of interest from kind of across the tech landscape in particular. It's definitely moved from niche to kind of almost like center stage in a lot of important research workflows related to AI.
You mentioned that the story of lean's changed and the time of your book, but I just want to make audiences really understand it's not like anything you wrote is outdated or incorrect or anything. It's just the story has grown. And I can't resist a really nerdy analogy here. It's sort of like you wrote the origin story of Wolverine when very few people were paying attention to X-Men. By the time your book came out, everyone was into X-Men and Wolverine was the favorite character. So it's sort of like you wrote the origin story before it became popular. That origin
Yeah.
story will always have the value. People will always want to know, how did Lean come to be? It's just that now Lean is even more enormous than when you were writing that story itself. So you were at the right place at the right time.
I like that very much. My own favorite analogy is Batman Begins. I love that movie, and I do think like you just like really see Lean wandering in the wilderness. Leo DeMora and this band of mathematicians wandering in the wilderness, and they achieve something, and suddenly it's like the superhero the world needs by the time they come back home.
Beyond mathematics, what other fields do you see this expanding into?
There are communities of people in physics and chemistry using Lean. I think one of the most promising efforts outside of mathematics is the creation of something called CSLib, Computer Science Lib, which is the computer science analog of MathLib, where they're trying to build up a repository of basic computer science definitions and results that can be used for two purposes. One is, I think there's this kind of confidence that it will be useful for formally verifying the correctness of software. So that original motivation Leo had when creating Lean, a motivation which is way more relevant now when we have way more code being generated by AI than we did then. Formally verifying the correctness of that AI generated code is important, and I think there's this confidence that having a CS lib to generate those proofs of correctness is going to be important. It's also going to be useful for just basic research in computer science. Computer science is also a proof-based research area, and so CS lib will provide practitioners in that area with the same kind of library foundation that has been so useful for Lean and mathematics.
Right. So there's a phenomenal question here that I cannot take credit for. Autumn wrote this, but I just have to make sure we get this recorded. 100 years from now, are we going to look back at Lean as a tool that has continued to grow, or really a discontinuity, like a historical juncture where something has really fundamentally changed in what mathematics is and how we do mathematics?
I think that is a very hard question to answer because mathematics is changing so much right now. I think the answer is either Lean will still be a part of mathematics, or something that is providing the same type of verification ability as Lean will be part of mathematics. It feels to me like inevitable and a perfect fit, and one that's only going to become more necessary as computers, AI are doing more math. So 100 years from now, will lean be a part of mathematics? I think lean or something like it, absolutely.
So now I want to voice a little bit of not doubt, but something in that direction, which is at the beginning, I
Just
likened
this
your
was a
book.
setup. That's what this was.
It
I
accidentally
didn't set
was.
this one up.
I
This
didn't
was a Noah
I
setup.
didn't plan it, but it's coming up. But yeah, so as I said, my favorite math book of all time is Chaos, and I put you in that category. I have to say, I reread Chaos recently, and there was an energy in the book that this was revolutionary, this new kind of way of doing science, this whole new framework. There was like departments of chaos that were emerging. And now where we are looking back 30 years later, I would say chaos is a very valid field in math, dynamical systems, ergodic theory, whatever, but it's no different than geometry or algebra and number theory. It's just a part of math. I don't think it changed the world or changed math the way people thought it would back in the 90s. I do have a slight feeling that lean may have a similar history. I don't know, and love to be wrong, that at this current moment, it feels like it's going to revolutionize math. And I could see 20 years from now, there will be a vibrant community of formal mathematicians who love doing this stuff. And there'll be 90% of the math community that just goes about their life and kind of ignores it. Just like I, as a mathematician, never use chaos theory. Does that seem plausible, or do you think I'm missing something?
Well, I think you're missing the biggest thing, which is how AI is transforming math. I mean, there is absolutely no future 20 years from now where AI has not transformed math. I mean, it is like shaking the field today. It's going to be shaking even more a year and 2 years from now. I think that seems like pretty certain at this point.
I'll agree
So
to that.
the question is not, does math go back to kind of the way it was in 20 years from now, people are working the way they were? No. AI is going to change math significantly. And the question is lean part of that change? And I think lean or something like it will have to be. So anyway, the question is like really, how does lean play with this much bigger macro trend that is in place now? I would just say that one thing I like we talked about at the beginning, one thing I really enjoyed about writing this story is it felt like a very human-driven effort, contingent on the right people, the right place at the right time. Since then, these more macro forces have taken over, which also promote lean and its use. But I think its ultimate long-term place in the field will be dictated by how these much larger forces play out.
I love that answer, and I just want to amplify it because I think that was very convincing, compelling. I think I was thinking of my life as a mathematician now versus 10 or 20 years ago before there was lean, and I could easily see continuing on my path without it. But I think you're absolutely spot on for saying, no, no, no. The comparison is 20 years from now when there is so much math being done by AI. Do you want to be able to verify it somehow, or do you just want to have gigabytes of math theorems that are AI written that nobody knows what to do with? So I think you're absolutely right. In the world where AI is a given, which I think is absolutely unquestionable, how can we live without this kind of verification? So I think that's a fantastic answer.
Good.
I have one thing that I want to add that I think you both are overlooking, not just with computers and machines. It's called the art of mathematics. And you need to integrate that humanity and the cleverness that people have that machines don't always think about. Because there could be this one cute proof or trick or I don't know, just something else that we're not seeing when we're just doing rigorous proofs and theorems and diving deep into this. Someone can always say, what if this? And it might even bring in a whole new field of mathematics that we haven't
Well,
thought about.
Autumn, that reminds me of one of my favorite anecdotes in your book. So maybe Kevin can elaborate on this a bit, which is as someone who hasn't used lean, I kind of thought, oh, it's this dry thing that takes all the life and energy. And as Autumn's rightly saying, kind of the art out of math, maybe even the understanding. But you have this amazing anecdote where Peter Schultze, this Fields medalist that you mentioned, he actually said he was formalizing a proof and he came to understand the key idea in the proof better by formalizing it. Do you want to elaborate on that a little?
Yeah, there's a lot to say here. I think, like anything related to computers and math or computers and anything and anything, it's kind of a double-edged sword. Sometimes if you are having AI generate math proofs, maybe you don't understand them and you lose an important element of human understanding. But a lean proof also facilitates it because you might have an idea that in your head is kind of like vague, you think it works. With lean, you have to really spell it out. You have to make sure you very crisply understand what it is you're talking about and how it relates to other parts of your argument. And Peter Schulze, through the process of doing that for this thing we call the liquid tensor experiment, very clearly having to think hard about what exactly do I mean at each stage in my proof, and trying to specify it at this language that works at the level that works in lean, did come to understand his own work better. And people view lean as a teaching tool in that way. You can understand proofs better once you have a lean proof. You kind of it's possible to kind of click into different elements of it and to kind of explore the logic of a proof in the way you can't with a static PDF. So there's, in fact, I think, a lot of potential for lean and formal mathematics to promote understanding if kind of used correctly.
That's the thing I keep coming back to. We spent this whole conversation asking whether a computer program could somehow flatten the art out of math. And what Kevin's book actually shows us is almost the opposite. The people who built this thing didn't lose the human part. They had to understand their own ideas more clearly than ever to make sure that lean would accept them. If you want the full story, the wandering into the wilderness years of science and technology, Leo DeMora, MathLib, all of it, the book is called The Proof in the Code, which is out now. So, Kevin, thank you for writing it. Thank you for being here. And as always, folks, stay curious and stay informed of the world around you. Until next time on Breaking Math.